Welcome to today's topic. Today we are continuing with diffraction. We already discussed about diffraction, the diffraction pattern obtained when a slit is exposed by a monochromatic light, and the diffraction pattern consists of central maximum. On either side of the central maximum we have secondary maxima and minima, and their positions also we discussed. Now we will discuss the comparison between interference pattern and diffraction pattern. That means double slit pattern and single slit pattern. Interference pattern, it occurs due to the superposition of light waves originating from two coherent sources. But diffraction pattern, it is due to the superposition of light waves originating from different points of the same wavefront or same source, we can say. So that is a point of comparison, or we can say point of distinction. That means in interference pattern we have two different or two separate sources. In diffraction pattern we have only one source, and we are discussing the superposition of waves from the different parts of the same source. And in interference pattern the width of all fringes are equal, and in diffraction pattern all fringes are not equally wide. That means you have central maximum which is very wide, and other maxima and minima are of decreasing width. Then next, that is all maxima are of same intensity in the case of interference pattern, but in the case of diffraction pattern central maximum is very bright and the secondary maxima are of falling intensity. That means first secondary maximum have intensity due to 1/3 of the slit. Secondary maximum have the intensity due to 1/5 of the slit, and third secondary maximum have the intensity due to 1/7 of the slit. Like that it goes. That means the secondary maxima are of decreasing intensity. And the next point is the dark bands, that is minima are almost completely dark in interference pattern, but in diffraction pattern dark bands are not completely dark. So the thing is this, the contrast between bright and dark fringes is very nice in the case of interference pattern, and it is very poor in the case of diffraction pattern. Okay, in the diffraction pattern we can say there is poor contrast between the bright and dark fringes. In interference, the pattern consists of large number of bands. In diffraction pattern, there are only few bands. The thing is this, even if the bands are formed, we cannot see them, we cannot identify them because of the poor contrast. So only the central maximum and the nearby one or two bands we can see. So these are the points of comparison between interference and diffraction fringes. The interference pattern formed during double slit experiment, actually it is obtained within the diffraction pattern due to one of the slits. That means both the slits will be forming diffraction pattern, and in the diffraction pattern of one of the slits the interference pattern will be formed. You can see as shown in the diagram, within the central maximum of the diffraction pattern, interference fringes are formed. Okay, but we do not experience this difference in intensity. You can see that in central maximum itself, the intensity is not unique. Okay, so that difference in intensity we are not experiencing. It's because of certain conditions which we maintain in conducting the double slit experiment. In order to obtain good interference pattern, we'll be obtaining the condition, that means the slit width which should be very, very small. So when we make the slit width very, very small, the width, that means the width of central maximum of single slit diffraction pattern, it increases. That means the width of diffraction maximum increases. When the width of the diffraction maximum increases, it gets almost flattened as shown in the figure. It gets almost flattened, and within that flattened central maximum we are getting the interference fringes. That is why we do not experience that difference in density among the interference fringes. We always perceive that interference fringes maxima, they are equally bright, and the dark fringes, they are equally dark, like that. It is because of this reason, because we always prefer the condition the slit width should be very, very small in order to obtain what sustainable interference pattern. When that condition is maintained, this also is achieved. That means the width of the central maximum of the diffraction pattern increases, and the central maximum, it gets almost widened, and within the central maximum we are getting interference fringes. Now for that concept, we have an example from the textbook, that is, what should be the width of each slit to obtain 10 maxima of double slit pattern within the central maximum of the single slit pattern. So you are asked to find the width of each slit, so that within the central maximum of the diffraction pattern, there are 10 fringes of interference pattern. In the central maximum, how many interference fringes are there? That means like this. This is the central maximum, no, that outer envelope. Within that central maximum, how many interference fringes are there? That is what is given. For that condition to obtain, for 10 fringes to be there within the central maximum, what should be the width of the slit? So what you have to do is equate the width of central maximum of the diffraction pattern with the 10 times fringe width of interference pattern. With that, you will get the width of each slit. That means 2 lambda d by a. That is the width of central maximum of diffraction pattern. That is equal to 10 lambda d by small letter d, where small letter d is the separation between the two slits in double slit pattern. So width of the central maximum is equal to 10 times the fringe width of interference pattern. So that capital letter d and lambda will get cancelled in the equation, and you will get a to be equal to, you can rearrange the equation, and you will get a is equal to 2d by 10. So we have a is equal to d by 5, that is 0.2 millimeter. So that is the answer. So this concept is very important. So we are getting the interference pattern within the single slit pattern, central maximum of the single slit pattern. In our discussion of diffraction at a single slit, we were considering the light to be coming to the slit, and from the slit the diffracted beam is going to long distance, and at a long distance we are keeping a screen. That's what we were discussing. But when we obtain such this diffraction fringes, the diffraction pattern will be very fade, because the intensity of the bright and dark fringes will be poor. We already stated there will be poor contrast, and since the distance at which the diffraction pattern is formed, that distance is large, because of that the intensity of that diffraction pattern will be poor. So to get good diffraction pattern, one important method we are following, that means we'll keep a convex lens in the path of diffracted beam. So as shown in the diagram, convex lens is placed in the path of the light coming from the slit after diffraction. So we are assuming the rays to be coming parallel to each other. So the rays, after coming through the convex lens, they will be focused in the focal plane. That means at the focal plane of the convex lens, we will get the diffraction pattern. Each set of parallel beams will be getting converged at different points of the focal plane. So we will be getting intense diffraction pattern. So we will have a doubt like, now will there be any path length difference for the waves when we keep a convex lens? Actually, when we keep a convex lens, as we know when we consider the distance or the time taken by the rays to come out of optically denser medium will be more, because the speed of light will be less in the denser medium. So that case is here, but for all the rays that the same time delay is taken place. Here one term optical path is there. In order to compensate for that time delay, actually we say like the distance to be traveled is increased. That means when a light ray, when it passes from air to a denser medium, suppose that denser medium is having a refractive index n, and if the thickness of that denser medium is delta x, so actual thickness is delta x. So actual path to be traveled by the light ray is delta x. But because of the high refractive index of that medium, we define the optical path to be n delta x. So actually what is happening is, because of this refractive index, high refractive index, speed of the wave is getting reduced. Because of this reduced speed, it has to travel for more time through that medium to come out of that medium. So time taken is more, but that time taken, that difference in time taken, we will speak in terms of increase in distance. So that term we use as optical path. So if delta x is the actual path, the optical path in that medium is n delta x, where n is the refractive index. So when we keep a convex lens of that much thickness delta x, for all the rays this optical path will be same. So when we look at the path difference while obtaining the conditions for interference fringes or diffraction fringes, we are concerned with the path difference. Okay, so path difference will be same because this optical path is the same for all the waves which are passing through the lens. Okay, so this is a practical method of obtaining diffraction pattern. So take care, while we do like this, we are getting or we are keeping the screen at the focus of the convex lens. So at the focal point of the convex lens, we are getting the diffraction pattern. So that point is to be noted. Note that the lens does not introduce any extra path difference in the parallel beam. This arrangement is often used since it gives more intensity than placing the screen far away. If f is the focal length of the lens, then we can easily work out the size of the central maximum. In terms of the angles, the separation of the central maximum from the first null of the diffraction pattern is lambda by a. First null means first secondary minimum. From the first secondary minimum to the center of the central maximum is lambda by a. The width of central maximum is 2 lambda by a. So the size on the screen will be what? F lambda by a. That means that capital letter D, the distance of the screen, becomes what? F, the focal length of the convex lens. So this is applicable when we keep the convex lens. Then the expression for the width of central maximum, it becomes 2 lambda f by a. Width of the central maximum, it becomes 2 lambda f by a. So note that point. So to conclude, see, to obtain good interference and diffraction pattern, we should keep A and D to be very small. A means width of the slit and D the separation between the two slits. So one example we are taking, the distance D between two slits, it should be of the order of a millimeter. So 1 millimeter or 1.5 millimeter, in that range the separation between the two slits will come, and the width of the slit should be even smaller than that. That means of the order 0.1 millimeter or 0.2 millimeter. So this should be the actual range of values for D and A to observe good interference or diffraction pattern. Now one problem from diffraction. A parallel beam of light of wavelength 500 nanometer falls on a narrow slit and the resulting diffraction pattern is observed on a screen 1 meter away. It is observed that the first minimum is at a distance of 2.5 millimeter from the center of the screen. Find the width of the slit. So it's given the position of first minimum. First minimum from the screen, from the center of the screen, it is given, and we are asked to find the width of the slit. That means A. Lambda is given, everything is given. So how we do this? So we know the angular position of the minimum. What about the angular position of the minima? We know the condition. The angular position of the minima are theta equal to n lambda by a, where n can take values like 1, 2, 3, etc. So for the first minimum, n is equal to 1 or theta is equal to lambda by a. If you know the angular position, what is the actual position of the first minimum on the screen? The actual position given by x is equal to this angular position into distance of the screen. Suppose capital letter D is the distance of the screen. So we can write x is equal to lambda d by a. So this is the expression for actual position of first minimum on the screen. That is x is equal to lambda d by a. So what all things are given? Lambda is given, capital letter D is given, x also is given, and what we need to find is only this a. So what is a is equal to? A is equal to what? Lambda d divided by x. So you need to substitute only in this expression. In here, instead of in the slide, instead of a, it is written small letter d. So it's enough to use small letter a, because in the textbook we have used small letter a. So we have a is equal to lambda d by x. Substituting for lambda d and x, we have the width of the slit to be 2 into 10 raised to minus 4 meter. That means it is actually 0.2 millimeter. With that, we conclude this session. Thank you.